Okay, the last topic for now in chemical change is energy changes in chemical reactions. So this becomes quite a bigger topic in grade 11 and 12, but for now you just need to learn the terms that belong with the energy changes. So one of the ways we know a chemical reaction has occurred as opposed to a physical change is that there's much larger energy changes, okay? And during a reaction, the kinetic energy of the particles changes during the reaction, and it changes a lot more than it does during a physical process. So when a reaction occurs, we have reactants and products, and these graphs will become very familiar to you. So if you look at a graph of energy versus the progress of the reaction or time, when you start a reaction with your reactants, it's like really difficult. It's like pushing a ball up a hill. But then once the ball gets to the top of the hill, everything happens really fast, okay? So often you need to input a little bit of energy to start a reaction. Like for instance, if you remember me setting fire to the magnesium ribbon. Once you've put that little bit of fire in there, the reaction carries on. The same with if you watch the video of the iron and the sulfur. They put the hot glass rod in to get this energy up to here, and then once they've put that energy in, the reaction carries on by itself, and those two examples both release a lot of heat. So you can see here the energy of the reactants is quite high and the energy of the reactants is quite low. So first you push all of the reactants up the hill, put some energy in, and then once the reaction starts, it will just carry on until you get to products. So this is what would happen with a reaction with an exothermic reaction. You can see heat is being given out at the end, okay? So this is also an exothermic reaction, and this is showing you what's actually happening to the bonds in the things that are reacting. This is an organic compound that's reacting. So it's see this chlorine here and this OH over here. This is a hydroxyl group. It is turning this into an alcohol. It's taking the chlorine off and turning this into an alcohol. So the chlorine comes off as an ion. And what happens is here, at the beginning, your reactants and your products have got strong bonds. That energy that goes in weakens the bonds so that they can then turn into different bonds. Remember, in a reaction, bonds are broken and bonds are formed. So here are your reactants. Here, bonds are being broken. That's what the energy goes in to do. And then new bonds are formed in the second half of the reaction. And you go from reactants to products. So you can work out how much energy has changed in the reaction. You work out how much energy you put in to break the bonds and how much energy you let out when the new bonds are formed. So the change in energy, remember delta, the triangle, is change. The change in energy is the energy absorbed to break the bonds, subtracted by the energy that is released when new bonds are formed. So you take in a certain amount of energy and you let out a certain amount of energy. Energy absorbed, energy released. So you can see here, this energy released here is greater than the energy absorbed. So if you look on the graph, small number, big number. So this reaction is releasing energy. It comes out with a negative answer, and that's an exothermic reaction. So when you have a look at the reaction, the final product can be colder or hotter. So if you give out energy, it's exothermic, and if energy is taken in, it is endothermic, and we measure this energy in kilojoules per mole. We're still coming to the mole concept, but kilojoules is like joules is a measure of energy, so it's kilojoules per mole. A mole is like the chemistry word for a dozen. Okay, so these are the two guidelines you need to the two definitions you need to remember from the guidelines. Endothermic reaction, energy is absorbed during the reaction. Exothermic reaction, energy is released during the reaction. So the graphs are slightly different. Remember the energy change. This now is an endothermic reaction. So remember, we had to take the energy absorbed to break the bonds. That's a big number. And here, when we release the energy to make the products, that's a small number. So my energy change here is positive. Okay. If we look at an exothermic reaction, the energy change is negative. The energy is coming out on the product side of the reaction. So If you have a look what's going on, an endothermic reaction releases less energy on the right than is absorbed on the left. So what happens is you've got reactants going to products. The reactants have strong bonds, but the products have weak bonds. So you put a lot of energy in, you get very little energy out. And the only example that's easy to think of is if you dissolve ammonium chloride. These packets, you break the packet, and then this endothermic reaction happens. They mix water with the ammonium chloride, and you get a little cold pack, a temporary cold pack. So in an exothermic reaction, this is sodium and water, more energy is on the right than on the left, because when the reactants go to products, there are weak bonds in the reactants and very strong, stable bonds in the products. So this has got a low energy input and a high energy output, as you can see by the fire. So we often describe these reactions in different ways. You need to recognize all of them. We'll come to this delta H next year. This is the change in the heat of the reaction. So like the other thing said delta E, but next year they'll start calling it delta H. So I'm just showing you this delta H here. So in an exothermic reaction, you will have reactants going to products, and energy is on the product side, okay? And they can either write plus energy, or they can write this delta H over here. Delta H is less than 0, just means delta H is negative. Or they can write it reactants go to products plus energy. This is just a number for the energy. So reactants go to products plus energy. Reactants go to products plus 20 kilojoules per mole. Can you see this is just a number for the word energy? Okay, so you need to recognize that if the energy is on the product side, it's exothermic. In an endothermic reaction, the energy is on the reactant side. It takes in energy. The reactants need extra energy to form the products. It has a positive heat of reaction, and here you can see exactly the same thing. Here's the energy, as the word energy, reactants and energy go to products. Here's reactants and a specific number for energy going to products. So you need to be able to apply this with a proper formula. So for instance, if they say sodium plus chlorine goes to sodium chloride plus 356 kilojoules per mole, then you know that's an exothermic reaction. Okay, if they write ammonium chloride plus water plus 20 kilojoules goes to ammonium chloride aqueous, then you know you've got an endothermic reaction, something like that. You need to be able to take this general writing and translate it. So check where the energy is on the side of the arrow, and you will be fine. Okay, I'm just going to briefly look at the reactions that are mentioned in the guidelines, exam guidelines in this topic that you should know. The first one is the decomposition of hydrogen peroxide to water and oxygen with a manganese dioxide catalyst. It speeds up the reaction but doesn't take part. I sent you a video of this, and you can check that the oxygen is collected by downward displacement of water. You fill a tube with water, and then you collect the gas, and it bubbles in here, and you can test it with a glowing splint. The next one is making water, and this is the reaction I said to you, I'm not actually sure that this is going to carry out well in real life. You have some zinc and acid, and a metal, a reactive metal and acid gives you hydrogen gas. You bubble the hydrogen gas out, and then you provide a little bit of energy with the candle, and this starts the reaction from the hydrogen and the oxygen going to water. But you're doing it against something that cools it, so you don't get the big boom. So this is a flask that's full of water from a tap that you keep cooling it. So I don't know how you're supposed to recycle this water on a lab bench, but hey. And then what happens is at the reaction here, where the water is formed from the reaction, not this water that's cooling it, okay, but the water that's formed from the reaction, that's the activation energy to start it is provided by the candle. This water then drips into some dry copper sulfate, and it turns blue, so you know water's been added. The next one is the synthesis reaction of iron and sulfur. So sulfur is this yellow powder. Iron filings are little black things. They make a yellow and black mixture. You can separate this by physical means, like for instance with a magnet. Here they've put the magnet on one side of a watch glass so that the metal doesn't stick to the magnet. But if you take this mixture and you heat it in a test tube, you will get a very strongly exothermic reaction, which makes lots of like heating and crackling noises. and you end up with this iron sulfide, which doesn't look like the mixture, and it's not attracted to the magnet afterwards. So you know that this is a completely different compound than what you started with. Then there is a precipitation reaction. We're going to look at this later in the next reactions in aqueous solution. So there's a colorless liquid, a colorless liquid. They happen to be lead nitride and potassium iodide. And then when you mix them together, they form this lovely yellow precipitate. It's a very cool reaction to watch. So you get the two colorless solutions mixing and this yellow solid forming. Here is the S for solid. So aqueous, 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 solid. The lead iodide is this yellow. And then sometimes you'll see this reaction, and instead of putting the solid here by the lead iodide, they'd put a downwards arrow. An upwards arrow is sometimes the formation of a gas, and a downwards arrow indicates that the precipitate is precipitating downwards. If you let this settle, you'll find all of the precipitate in the bottom of the container. Then there's the titration of hydrochloric acid with sodium hydroxide to measure the change in temperature. A titration is just where you find the concentration of an unknown solution using some really well calibrated, very accurate glassware. You use a burette here. And in grade 10, what you're supposed to do is mix hydrochloric acid and sodium hydroxide, and they go to sodium chloride and water and energy. So the energy is on the product side. This is exothermic. So you put, like, for instance, the acid inside something like a polystyrene cup that keeps the heat in, and you put a thermometer in here, and then you read the thermometer as you keep adding the acid to the sodium hydroxide. And then there's something in there that changes color to say the reaction's finished. And so when you do that, you can measure the temperature to prove that this reaction produces heat. You can also put your hand on the container and feel it getting hot and know that there's a reaction happening. These are the proper equipment for it. This is the pipette for accurate measurement of the one solution. Here's the burette for the accurate measurement of the other solution. You take an initial reading, you take a final reading. When your indicator changes colors, when you take the final reading, and then you do calculations. We'll get good at calculations later. And that's the end of this part of the topic.